Welcome to today's lecture, which is on speed governors on prime movers. We'll mainly look at group characteristics of governors. The learning objectives of this lecture is on this. We'll look at basic working principles of the centrifugal hydraulic governor. Explain the reason and mechanism. Understand the effects of changes in troop setting. If troop settings are changed, what will be the effect, we can see. And understand how reverse power protection is tested. This reverse power protection is something which is frequently tested on board the ship, and how it takes place or how the testing takes place can be understood in the context of the droop graph. We'll also see what is the reason for compensation in governors. This class is meant for college students as well as engineers on board, both at operational and management level. A governor is a part of the vessel's engine which is studied throughout. It is studied, so it is not an unfamiliar equipment. There are certain principles in that which are not clearly understood. The purpose of the lecture is to focus on those things. To start with, all speed governors are controllers of speed. So what we mean by speed is mainly RPM of the prime mover. There are two types of governors. One is called speed limiting governor, which in marine vessels are fitted in old main engines to prevent RPM going above a set value. So this is what you see in vehicles also. If you see in many commercial vehicles, it will be written speed governor is fitted. So this speed governor is a limiting governor. Apart from these, what we normally discuss are all speed regulating governor. Speed regulating governor means it will ensure the speed doesn't cross a particular value, doesn't go above, doesn't go below, like that. So it is meant to maintain the speed. Our discussion is only about regulating governor. We look at quickly comparison. This is a centrifugal mechanical governor is there, and centrifugal hydraulic governors are there. Electronic governors are there, and you also have governors which are built into the engine control. That means it will not be identifiable separately as a governor. So in these modern camshaftless and electronically controlled engines, the governor is not a different or a separate discrete equipment. It is built into the engine control. Like we said, our main discussion is on this, on the hydraulic governor, for the sake of understanding the mechanism. But whatever principles are discussed here, they are common to all kinds of governors. The principle of droop and compensation and similar sensitivity and these kind of things, they apply to all kinds of governors. The method will vary from type to type. So if you look at, as far as speed is controlled, there are two types of governors. One is called as isochronous governor. In an isochronous governor, the speed will be maintained as a set speed. That means if the load changes, if more kilowatt is drawn from the prime mover or less kilowatt is drawn from the prime mover, the speed will be maintained the same. That is called isochronous. When we say speed is maintained the same, it does not mean speed will not change at all. In any kind of control application, whenever there is a disturbance, the value will change. but it will recover back. So if I have an alternator running at 60 hertz and it is controlled by an isochronous governor, it means if the kilowatt is increased or decreased, it will still maintain 60 hertz. Finally, it will maintain 60 hertz. That is the meaning of isochronous. So when load changes, final steady speed will be the same as the steady speed. So the governor is a equipment which works very fast. So what we mean by final steady speed will be achieved in a matter of seconds, very short period. So if you have a governor with speed droop, then the difference is it will allow the speed to drop below the set speed as the load will increase. So as the load on the engine keeps on increasing, the set speed will become or the actual speed will become lower. That is called governor with the speed droop. There is a setting in the governor which will allow you to change the droop. There is a droop adjustment in the governor. All the engineers who sailed on board would have seen this. So there is a droop adjustment which we can adjust as required. This is a picture of a well-known Woodward UG8 governor. This motor on top is for setting the speed. So this motor will rotate clockwise or anti-clockwise, and through this vertical shaft which you are seeing, the spring compression inside the governor will be altered. So this is how speed setting is changed. This is the output shaft which is connecting to the fuel linkage, fuel lever. This is a drain. This is a hydraulic governor with its own oil filled up inside. So this is a drain plug for the oil. And this is what is called as a compensation needle valve. Compensation needle valve plug. So if you look closely at the front of this, you can see these parts. This is the speed setting, speed droop setting. It is showing in percentage, 0 to 10 like this. So currently it is something like 30%. So 30% droop setting means it is 30% of the maximum possible droop setting. So the maximum possible droop setting could be 4%. So right now it is 30% of 4% is the amount of droop that is set. So typically it will be here between 30 to 50, the usual setting you will see in the droop. What do these mean? We will see. This is a local speed adjustment. This many of you would have seen. By turning the knob in this direction, the speed is changed. That is, this is parallel to your motor. Like when the motor is not functional, you can change the setting from this. Similarly, clockwise means it will increase. This is an indicator which shows how many times this is turning, in which way this is turning. So this is the adjusting knob, this is the indicator. This is a load limiter, which all of you know. It is to prevent the fuel going beyond certain values. So the upper limit for power can be set by this. So the fuel can be set by this. So coming to what is an isochronous governor? How does it work? It is like this. This is the spring, centrifugal governor speeder spring, we call it. The spring force is adjusted by the motor on top. The governor works by the principle that it is, this entire mechanism is driven, rotation you can see, and these are the flyweights which are going to be going around. and this centrifugal force acting on the flyweight acts this way. So there is this two forces which are being balanced. One is a spring force from acting downwards, and here is the component of the centrifugal force. The centrifugal force which will act this way. So when this force and this force are balanced, this entire mechanism will be at a steady position, at a constant position. If these two forces differ, this part will move. And here is the hydraulic oil coming from an attached pump inside the governor. This hydraulic oil will be directed towards this part, which is called as the power piston. If the power piston moves in this direction, the fuel will increase. This valve is called as the pilot valve. So if the pilot valve goes down, hydraulic oil will flow into the power piston cylinder arrangement. If the pilot valve moves up, the oil from here will be going to the drain. This is the simple working principle of the centrifugal governor. So how it is going to work is the speed setting is by compression of the spring. Then the spring force is balanced by the component of the centrifugal force. That is this red colored force which we are seeing. The component of the centrifugal force acts this way through this mechanism called the bell crank. And when the speed setting is changed, what will be the result? For example, the spring force is increased. When the spring force is increased, what will happen is this pilot valve will be pushed down. As the pilot valve is pushed down, then the oil will flow from here into the power piston and the fuel will get increased. As the fuel is increased, the speed of the engine will increase again. And as the engine speed increases, centrifugal force will increase once more. And these two forces will be once again balanced. That means the spring force and the force of this will be balanced. How this spring force is increases because compression is increased. How is the centrifugal force increased at steady state? This point will move further away because of this bell crank mechanism. It will be moving further away. So what we need to understand here is, I asked for a increased speed from 720 RPM. I want to increase it to 725. That means this spring will be compressed, and as the spring is compressed, this force will increase. Engine will pick up. As this part goes down, fuel will flow into this. As the fuel flows into this part, the engine speed will again increase, and from 720, the engine RPM will be increased to 725. At 725, both these forces will be once again balanced. So in this example, fuel will be more than before, and the speed also will be more than before. Instead of running at 720, it will be running at 725. And when will this become steady? When this pilot valve blocks the passage. The pilot valve is here. It blocks the passage and prevents oil from flowing into the cylinder or draining from the cylinder. That is when this finally reaches a steady speed. So what this means is, if I ask for a particular speed, if I say I want 720, then the 720 will be maintained all the time, even when the load is changing. This part we can understand when you see the next line. So imagine that I want the speed only 720, but the load is increasing. When the load increases, what will happen is the speed of the engine will come down. How the speed of the engine comes down, we'll see in the coming slides. But the speed of the engine will come down. As the speed of the engine comes down, the centrifugal force will reduce. If the centrifugal force reduces, pilot valve will go down. And once again, the same sequence will take place. That means hydraulic oil flows into the cylinder and the fuel is increased. As the fuel is increased, the engine speed will once again pick up. But the difference now is there is no change in the speed setting. You ask for 720 RPM, same 720 RPM will be maintained, but the fuel will be more. Why is the fuel more? It is to take care of the increased load. So in both these examples, the previous slide and this slide, what we are seeing is that if your pilot valve arrangement is like this, then whatever speed you set, whether the load increases or decreases, whatever speed is set, that speed will be achieved. Kilowatt, it will maintain the same speed, whatever speed is set. If the set speed is changed, instead of 720 RPM, if you want to increase it to more, then the speed will change. Otherwise, for a particular set speed, load change does not affect the RPM. That is the meaning of isochronous. So isochronous means if you see here, kilowatt of the, or if you take an alternator as an example, the kilowatt of the alternator goes from 0 to 100%, RPM will be maintained the same as you see in blue color. This is called isochronous. If you say there is droop, then as the load increases, the speed will come down. So why the speed is coming down will be seen. But to understand this whole process, start like this. Imagine there is an alternator which is starting up after a blackout. There is a complete blackout on board your vessel. So a single alternator has been started. You have adjusted the frequency to 60 hertz. So it is come here. It has come down to 60 hertz. And at 60 hertz, the circuit breaker is closed. So the kilowatt is still 0. It is running at 60 hertz frequency. Then what we do is you go and start more and more electrical motors. As more and more electrical load is added, what will happen is alternator's output current will increase. So the current of the alternator starts increasing. What is the reason for the current increasing? Is this. It is due to the reduction in overall circuit impedance. Like one of the principles everyone will understand that if you add resistance in series, overall resistance will increase. If you add the same resistances in parallel, then the overall resistance will come down. So all loads that you are connecting, whether when one motor running and you start another motor, all loads that are connected are always connected in parallel. So because loads are connected in parallel, the overall impedance in the circuit will come down. And since the overall impedance is coming down, current will start increasing. So this is the simple principle by which when you add more load, the alternator current increases. So when the alternator current increases, the next part is that stator magnet will become stronger. Everyone understands that in an alternator, in the stator also there will be a magnet, which is a rotating magnet which rotates at synchronous speed. So the strength of this stator magnet also increases. Now this rotating magnet will lag behind the rotor magnet. Rotor magnet is what is there in the field which the engine is rotating. So the rotating magnetic field in the stator will be lagging behind the rotor magnet by an angle which is called as load angle. So what you have is the north pole and the south pole which are slightly displaced from the radial direction, and this is what will produce a torque. So this torque is opposed, it will oppose the rotation of the engine. So in the previous classes, once before we had discussed that whenever we talk of Newton's third law and say that applied torque is equal to opposing torque. Opposing torque, part of the opposing torque is for energy transfer. So this magnetic torque which we talk about in an alternator, this is the one by which energy is converted from mechanical to electrical. So from the mechanical power given to the rotor, it becomes electrical power in the stator due to this magnetic torque. Remember, magnetic torque works in both motor and alternator. The difference is in a motor, it will be in the running direction, and in an alternator, it will be in the opposite direction. And it is a magnetic torque which is responsible for energy transfer from one form to another form. So what all this means is that as the current increases, it means as you start more and more motors, the magnetic torque on the alternator is going to increase. As the magnetic torque on the alternator increases, the engine will slow down. How this slowing down happens, you can again see here. At any steady state, applied torque from the engine will be equal to the opposing torque. This is for any rotating machinery. Opposing torque consists of these. One is I into alpha. I is second moment of mass and alpha is angular acceleration. There is frictional torque and there is magnetic torque. So this part is only for, this is for due to inertia. It matters only during change of speed. This is always there due to friction. This is responsible for energy transfer or doing work. Now what is going to happen in this equation is, as the load increases, this part will increase. Magnetic torque will increase. So if the magnetic torque increases, the opposing torque becomes more than the applied torque. If the right hand side is becoming more, the left is remaining same, then this part has to come down. This part, this is the this whole factor. So this has to reduce, or this has to become negative, or that is how the engine slows down. So we say alpha becomes negative. Alpha becoming negative means engine will slow down. So this is a somewhat technical way of explaining that as more and more load is added to the electrical circuit, the engine is going to slow down. So once the engine slows down, the governor will react. And the governor reacts, it increases the fuel and the engine torque will increase. Once again, it can restore the balance. But the issue is what will be the speed. In the case of isochronous, the final speed will be the same as the initial speed. The frequency will be to 60 Hertz. So what I am trying to tell is that whether you have isochronous setting or with some droop, the governor will handle additional load. So as more load is brought in, governor will definitely increase fuel for the engine, and the generator engine will be able to supply power for the additional load. The difference lies in what will be the speed that is maintained. If you have an isochronous setting in the governor, then the initial speed will be maintained throughout. If you allow droop, then as the load increases, frequency will come down. So how this change happens is like this. This is called the droop link or the droop arrangement, this extra part. This was not there in the previous drawing. So what happens with this is, you can see very easily, if the load increases, speed will come down, pilot valve will go down, and the hydraulic oil will flow like this. and fuel is going to increase. Now, what is going to happen is, as this part goes up, this lever will move. This lever, which is called as a droop lever. This droop lever has got a fulcrum here. The fulcrum is here, and you are moving this part. The whole lever will take an angle like this. The lever will turn, become this way. So if the lever goes this way, the force on the spring will become reduced. So what happens is, with increasing load, fuel will be increased as before. There is no difference in that. Fuel will once again be increased. But what happens is, the spring compression will reduce now. And spring compression is the set point for speed. So what is this mechanism achieving is that with an increased fuel or increased load, the speed set point is brought down. In other ways, you are telling the governor that as I keep increasing kilowatt, you don't have to maintain 60 hertz. You can allow the frequency to come down by a small amount. So it is the droop in a governor is not a defect in the governor. It is a deliberately set feature. So when we want, we will allow the governor to run at reduced speeds as the load increases more and more. So that is how this mechanism is. This is a schematic drawing. Actual construction is a little more complicated, but this explains the principle. How much will be the droop setting is changed here. So if you make the droop setting 0, then the movement of this lever will not make any difference to the spring. This is how droop is given. So because of this droop, even though the fuel is increased and the engine is handling more kilowatt, the steady speed will be a little bit less. So in the case of this alternator, this is what is going to happen. As the load keeps on increasing, speed will keep coming down. So if the engine is running at this much kilowatt, the speed will be here. How will you restore the speed to 60 hertz? Then you have to again turn the motor which is on the governor, which is a speed setting knob which we have in the control room. So by adjusting that, this entire line can be brought up like this. So this point will move to here, and the frequency will be again 60. If you don't make that adjustment, it will remain here. And the meaning of 2% droop setting is, if you keep on increasing, it will keep going down. You can see it in this example. So once again, we start the same way. Start with the single alternator. It is started and connected to a dead switch board. Now assume that the governor has got a droop setting of, let us say, 2%. Then as more and more load is added, the droop link will reduce the speed setting. And the speed setting, since this droop speed setting is reduced, actual speed of the engine will come down. And the meaning of 2% is, at 100% load, the speed would have come down by 2%. It will be here. So once again, if the engineer wants to restore the speed to 60 hertz, he will move the speed adjusting lever in the switchboard, which will rotate the motor on top of the governor, and the spring force will be increased. And this whole red line will move further up, so that this point will come here. And the red line will be in a position like this now. So let us move on to parallel operation. Now, one other question that is asked is that if a machine engine runs alone, is it okay to have it with zero droop? So commonly, it is said that if a single running machine does not need to have droop, but either it should have droop or it should have compensation. Otherwise, what happens is that governor is a machine with very fast response, and the engine is much slower in responding. So if you don't have either droop or compensation, it will create a lot of disturbance in the operation of the engine. That is why even many of you would have seen, even your main engine is most of the time a single running engine. But even for a main engine governor, if you go and see, there will be a droop setting. It is not zero. So even though we say that single running machine can run without droop, practically it is not done that way. Even single running machines have a droop setting. Okay, so but main issue is parallel operation. So what is the meaning of parallel operation? You look at it like this. It is not related to generators or any other alone. It applies in lot of other systems. It applies to mechanical, electrical, and other systems. So if you run two pumps in parallel, will you agree this point that at the point where the two pipes meet, pressure must be same? You cannot have two different pressures where the two discharge pipelines join. But the flow rates can be different. One pump can supply more liquid, other pump can supply less liquid. But where the pipes join, it has to have the same pressure. Individual pump discharge pressure can be different. But where they join, at that point, the pressure cannot be different. You cannot, in one point in a pipeline, you cannot have two different pressure readings. That's a simple meaning. Same way, if two generators are running in parallel, where they are connecting together, finally, where is the connection taking place? It is at the switchboard. At the switchboard, their voltages has to be same. You cannot have two different voltages at that point. But what is the generated EMF? Generated EMF is what is internal in the alternator. That can be different. It is same like saying individual pump discharge pressure can be different. So pump discharge pressure can be different. Same way generator EMF can be different. But just like you say, where the pipeline join, pressure should be same, here voltages must be same. Again, just like you say, pumps can have different flow rates, parallel operation can have different current. So when two alternators run in parallel, it is all right for them to have different current values, but they will always have same terminal voltage. They can also have different EMF. So EMF in the generator is different, terminal voltage is something else. And parallel running machines must have same terminal voltage. And it is not a difficult principle to understand if you think of pumps running in parallel. It is very similar. Now to understand this, you think like this. There are two separate batteries, independent batteries are there. This is a battery with it's a 9-volt battery supplying a load like this. This is a 6-volt battery which is supplying a load like this. They are independent cycles. Now if you connect the two batteries together, then what will happen? You connect them in parallel. Now can you have 6 volts and 9 volts here? Is it possible after connecting them in parallel? Not possible. At the same point in an electrical circuit, you cannot have two different voltages. So what will happen now is once you connect them together, the terminal voltage cannot be different. Independently, one can have 6, another can have 9. But if you connect them together, they must have same terminal voltage. Current will be different. Current supplied by one battery and the other will be different. The common terminal voltage will be a value between 6 and 9. And if the internal resistance of the batteries are same, in that case, the voltage will become 7.5. There is a calculation you can see. In electricity, it will come between the same. It will be 7.5, which is average of these two. So current will flow differently in the two batteries. Now coming to AC, DC is a little simple because DC voltage doesn't change with time. But what is the problem with AC voltage? AC voltage is not fixed. It is going to change with time. So what matters in AC is called instantaneous voltage. And we should always have a condition where instantaneous voltages are same. To make sure instantaneous voltages are same, the frequency must be same in both of them. So for example, if you see blue line is the waveform of one alternator, and if the red line is the waveform of the other alternator, which is running in parallel, the difference between the two is their frequency is not same. If the frequency is not same, you will get difference in the voltage.
Sorry for the
first, what will happen then? In these conditions, what will happen is current will circulate. The circulating current is called synchronizing current, and the synchronized current will not allow the alternator to run at two different frequencies. So one of the very important rules with parallel running alternators is parallel running alternator must run with the same frequency all the time. They cannot run at two different frequencies. And their terminal voltage waveforms must be always matching. They will exactly match. Anytime there is a difference, it will correct internally. Electrically, it will correct. So when you keep this principle in mind, next point will be easy to understand. Again, this is also not complicated. If two engines are connected mechanically by a gearbox, the two engines are connected together with a gearbox. Will it be possible for one engine alone to slow down? What do you think?
No, sir.
It is not possible. So they are mechanically coupled together, and they can either slow down together or they will increase together. It is impossible for one alone to increase or decrease. Here it is exactly same. These are magnetically coupled. So it is not possible for two parallel running alternators to run at different frequencies. So from this, the rest of it will follow. Now you see how load is shared. The black line shows a running alternator. The current load is 600 kilowatt. Frequency is 60 hertz. It is running at 60 hertz and 600 kilowatt. So this point represents the current condition or the present condition. Then what is done is you start the second generator, which is shown by the blue line. Second alternator is started. Its kilowatt is 0, not yet on load, and you synchronize it and close the circuit breaker here. So this point represents the closing of the circuit breaker. Then how do we shift the load? What is done on board the ship? On the ship, we have the speed adjusting lever on the switchboard. And for the incoming generator, we turn the lever in the increased direction. That means you are changing the set point of the incoming generator's governor. That means this blue line will move up. You are actually moving this point. The blue line will move up. And what do you do to the other generator? The running generator? You will move down.
Reduce.
You will reduce. That means this point is brought down. So what happens is number 2 setting is increased and number 1 setting is reduced, and you get an intersecting point like this. What does this intersecting point represent? It represents the running position. So these one line has gone up, other line has come down. This is the intersecting point. The intersecting points gives the share of the load, that how many kilowatt is shared to is on number 1 generator and how many kilowatt is on number 2 generator. And it also gives the busbar frequency. So in any parallel running alternator, the droop lines where they intersect gives the running condition. And what are we calling by running condition is this many kilowatt is on the incoming generator, which is number 2. For example, this can be something like 200 kilowatt, and 400 kilowatt is remaining on number 1 alternator. And the busbar frequency is here.
Moderator here, Mr. Venkatesh,
Like
sir.
this. Excuse me?
Venkatesh, sir, moderator here. Sorry for the interruption. We can have a poll for few seconds now, sir.
Go ahead. No problem.
Thank you, sir.
This is also the only point with a common frequency. So because the important point is parallel running machines have to run with the same frequency. So where is the frequency constant or same in both of them? Can it be here anywhere?
Intersecting points.
The only point where the frequencies are same is the intersecting point. And this is the only point at which it will run. So the advantage of this is, unless the engineer or the power management system alters the speed setting. How do you change the speed setting?
By the speed of the motor.
By the speed of motor. Unless the speed of motor is rotated, unless these 2 points move, then the load cannot shift, because the 2 alternators cannot run at any other point. They can run only here. Because of this, there will be no random shift of load. We will give it, there will be stability. That means if I want this generator to take 400 kilowatt, it will continue to take 400, and this will take 200, and it will remain like this. Without this, you will get instability. That you will see in the coming slides. Now the droop line also shows how reverse power trip is tested. How do we test reverse power? It is like this. You want to test reverse power on number 1 alternator. Number 1 alternator is shown by the black line. So this point shows number 1 speed setting is reduced till the kilowatt has become 0. So here it has become 0. It is not producing any electrical power, but the engine is still consuming fuel. Why is it consuming fuel?
To overcome frictional resistance.
Because there is resistance. The resistance is still there. Now, if I reduce to simulate the reverse power, what we normally do is we reduce the setting even further. That means this black line is moved even further. So, number 1 generator, we reduce the speed setting even more. So, as you reduce it even more, what will happen is I am reducing the fuel to the engine, but the speed is still maintained. Engine is not slowing down. How is that possible?
Because sir, second generator which is running, that drives the first one.
Correct. So the energy required to keep rotating is now coming partly from the other generator. So for example, if you think that at this point, with 0 electrical power, if you think that 100 kilowatt is required for overcoming friction, then here what is happening is minus 50 is the power. That means out of this 100 kilowatt which is required to overcome friction, 50 is still coming from the engine, but 50 has to come from the other generator. So we say number 1 power has become negative, or your alternator is turned into a motor. So this is a condition we always call as motoring. Motoring means your alternator is drawing electrical power and it is producing mechanical power. Now in this condition, if you allow the engine to keep running, all it means is that the fuel to the engine is reduced below idling levels. Still the engine is continuing to run because alternator is giving the additional mechanical power. What will be the running direction of the engine?
Same, sir.
Or
Same.
It has to be exactly same?
It has to be exactly same.
Exactly same. Will the speed be different?
No, sir.
No, sir.
It is also exactly same. So all that has happened is that even though I have brought the fuel below idling level, engine is still running at the same speed. This is the motoring condition. Now, what is if this itself is not harmful in the sense that alternator is now turned into a motor and it is assisting the engine in rotation. That is all there is. But what this means is, suppose I reduce the fuel to completely zero, then what will happen?
Will continue running.
It will still continue to run. It is not going to stop. Why?
Because the other one drives it.
Other one will drive through the alternator as a motor. It will keep developing the torque to overcome resistance. So what this means is like this. Imagine a single alternator running and there is a fault in your engine. Easiest fault to understand is low loop valve pressure. So low loop valve pressure takes place because of a clogged filter or something. Low loop valve trip will activate, fuel will get cut off and the engine will stop. Because of this, damage to the engine will be prevented. Now, if same problem happens in parallel running. Parallel running condition, the loop valve pressure drops. Why does the loop valve pressure drop? Because of a clogged filter or because there is no oil in your sump. Then the trip will act, fuel will be cut off, but will the engine stop?
No, sir.
It will not stop because the alternator will keep driving it. So what is necessary for us is you must disconnect. Again, mechanical example is easy. If you have two engines coupled together and they're driving a common load such as a propeller, can you stop one engine alone?
No, sir.
Not possible. So what will happen if lube oil fails in one engine? The low lube oil trip will stop the fuel, but you also have to disconnect. So same low lube oil trip will also disconnect the engine. How do you disconnect the engine? By declutching. A clutch mechanism has to be there and it will declutch. So if you compare with the alternator, it is a very simple comparison. Where do you disconnect here? Is there a clutch between engine and alternator?
Circuit breaker.
No, there is no clutch between the engine and alternator. So the easiest way to disconnect is the circuit breaker. So by disconnecting the circuit breaker, you are allowing the engine to come to a stop. You are protecting damage to the engine. This is the way you have to understand reverse power protection. And it is done by the reverse power relay detects this. So power is becoming reverse is a very simple thing to understand. Why does the power become reverse? It will become reverse only when the fuel is reduced below the idling levels. And a normal circumstance, this should happen because of a fault or because the fuel filter is clogged. Any such reason. We are simulating the same thing by deliberately reducing the fuel. So it is like same thing. It's once again repeated. If a single prime mover is running, it can be stopped by cutting off fuel. If it is running in parallel, you have to disconnect. Otherwise, serious damage will result as safety shutdown will not save the machine. In mechanically coupled system, disconnection at the clutch. In the case of alternator, it is done at the AC. This is the easiest way to understand why reverse power protection is right. Now coming to this isochronous condition. So what are the rule for running in parallel as far as frequency is concerned?
Has to be same.
Has to be exactly same. Now if both alternator engines are isochronous, then at every single point the frequency is same. So it is possible to run here, it is possible to run here, you run here, any such position is possible. This will definitely lead to severe instability. It can go to a level, it very often can go to a level where all the power will go on one alternator and the other will go into zero or even motoring condition. So if you don't want instability, point is simple, there must be a single intersecting point. A single intersecting point which will say this is the bus bar frequency. So how to achieve this? You can run with both with the droop, which is the most common arrangement, or you can have one with isochronous and the other with droop. So if I have one isochronous, it will be a horizontal line, other is with an angle, and you'll still get a single intersecting point. If you have one isochronous, other with droop, then it is like this. Then the change in load will only go to the alternator with zero droop.
Mr. Venkateshan, sir.
Yep.
2 minutes are left, sir.
Fine.
And just I will inform the candidates. Please vote in your poll, which is appear in your screen. Thanks.
Right. The compensation, what is the meaning of compensation?
It is to make the governor achieve the speed more fast and in stable condition, not to overshoot or undershoot.
Compensation is provided to reduce hunting. Why does hunting take place in a governor system? Is because, or any control system, is because the gain of the controller is high and the system is slow to respond. Often that will be the reason. Between the engine and the governor, governor is fast to react, but the engine will be much slower because of the inertia. So what is going to happen is if the fuel, if the load on the engine increases and because of that the speed comes down, and when the speed comes down, fuel is increased. The engine will not pick up speed immediately. Due to this, what is going to happen is the governor will keep on increasing the fuel. And when the engine response starts, it will create an overshoot condition. The speed will go to the other side. So since the slowness of the engine cannot be compensated, what you need to do is to bring down the speed of the governor or to make the governor respond a little more slowly. So it is used for reducing gain. This is the meaning. As the governor is fast and the engine is slow to respond. So what we say is that compensation is for handling a different problem. This is called temporary droop. Temporary droop means as the load is increased, how much is the speed coming down? You don't want the speed to come down too much. At the same time, if you try to restrict it too much, then it will be hunting all the time. So another way of telling will be compensation is for controlling the gain of your governor, or it is for controlling the sensitivity of the governor. So how do you provide compensation? So the compensation is given this way. If you see this part, this is the hydraulic oil, this is a pilot valve. Output from the pilot valve is going to this part called the buffer piston and then to the power piston. But this oil is also allowed to come here, act on this part which is called as a compensation line. So this is an additional part which is not there in the previous diagram. So what this means is as the pilot valve goes down, hydraulic oil move towards moving the power piston. But the same hydraulic oil will also act on this part. And because it is acting on this part, it will move the pilot valve up again. So the normal meaning of the working principle is, if the pilot valve goes down because of drop in speed, when should it come back? When should it start moving up? Only when the engine speed increases. Engine speed increases, only then the pilot valve should move up. But in this case, what is happening is the same hydraulic coil is used for increasing the moving the pilot valve. Or another way, it is like you are telling the governor that the engine speed is already increasing. Because the pilot valves will move upwards again, what will happen is that the fuel going to the engine will be controlled. So this is called negative feedback. The negative feedback always means whenever you use negative feedback, the gain is reduced. Normally you use negative feedback in systems where the gain is too high already. The amount of negative feedback can be controlled by this valve called the needle valve. This is called the compensating needle valve. Suppose I open this valve quite a bit, then this oil will act on both sides, this side as well as this side. That means the compensation will be very little. If you reduce the compensation, then the governor will be sensitive and it will hunt. So the more I open this valve, more the governor will cause hunting. If I tighten it, then it will become too much a compensation and will result in hunting. It will result in sluggish behavior. If you tighten this too much, it will result in sluggish behavior. So normally this has to be adjusted on board the vessel according to the engine, or after doing maintenance to the governor. All these times you have to set this. So to repeat or to explain the difference between droop setting and compensation. Compensation is for temporary droop, or it is to control the amount of hunting that takes place. Droop is for controlling the permanent values, the permanent change in setting.